You're standing in a museum, staring at the massive skull of a saber-toothed cat, and the tour guide says something that stops you cold. This creature went extinct because it couldn't adapt. But here's what they don't tell you. This animal survived for over 42 million years across multiple ice ages, continental shifts, and dramatic climate changes. The saber-toothed cats weren't dinosaurs, but their story reveals something extraordinary about how apex predators actually work. And it connects directly to one of the most misunderstood predators from the age of dinosaurs. Because 70 million years before Smilodon prowled the Americas, there was another saber-toothed hunter that rewrote the rules of predation entirely. And it wasn't even a mammal. Welcome to the untold story of Convergent evolution's most spectacular success and how paleontologists in 2025 are using cutting-edge biomechanical analysis to finally understand what made these prehistoric hunters so devastatingly effective. If you're fascinated by the science of ancient predators and want to see more deep dives into paleontology's greatest mysteries, hit that subscribe button, because we're about to explore something that connects the age of dinosaurs to the Ice Age in ways scientists never expected. Let's rewind to the late Permian period, approximately 260 million years ago, long before the first dinosaurs walked the Earth. The supercontinent Pangaea dominates the globe, and the climate is harsh. Extreme seasonal variations, vast deserts in the interior, and ecosystems still recovering from earlier extinction events. This is when the first saber-toothed predator emerges, but it's not what you'd expect. Meet the gorgonopsids, a group of therapsids, distant relatives of modern mammals, that developed elongated canine teeth independently, millions of years before true mammals even existed. The largest of these, Inostransevia, stretched nearly 12 feet in length and possessed saber teeth that could reach up to 5 inches long. Fossil evidence from Russia's Permian deposits shows us something remarkable. These weren't just oversized teeth for show. Bite mark analysis published in 2024 revealed that gorgonopsids used a precision killing technique, targeting the throat and major blood vessels of their prey with surgical accuracy. But here's where it gets interesting. The biomechanics of their bite were completely different from what would evolve later in mammalian saber-tooths. Scientists at the University of Bristol used finite element analysis in 2025 to test digital models of Inostransevia skulls under simulated bite forces. What they discovered challenged everything we thought we knew about saber-tooth hunting strategies. Unlike the shearing bite of later saber-toothed cats, gorgonopsids used a canine shear bite, where the elongated teeth acted more like daggers during a controlled, powerful snap. The jaw muscles weren't positioned for maximum bite force. Instead, they were optimized for speed and precision. This predator wasn't crushing bones. It was performing calculated strikes to vital areas, then backing away to let blood loss do the work. But that was only the beginning of the mystery, because the gorgonopsids went extinct in the Permian Triassic extinction event, the most catastrophic mass extinction in Earth's history. 90% of all species vanished. The saber-tooth strategy seemed to die with them until evolution tried the experiment again. Fast forward to the Middle Triassic, around 235 million years ago. Dinosaurs are just beginning to emerge as a distinct group, still small and relatively insignificant in ecosystems dominated by other reptiles. Among these competitors are the reinventing, massive crocodile-like predators that ruled as apex hunters before dinosaurs took over. And here's the twist. Some of them independently evolved saber-like teeth. Saber-Tooth, a 23-foot-long predator from what is now Argentina, possessed recurved, blade-like teeth in the front of its jaws. While not as dramatically elongated as true saber teeth, fossil analysis shows these teeth were used for precision strikes against large prey. CT scanning of Saurosuchus skulls in 2023 revealed that the attachment points for jaw muscles were positioned to deliver rapid, slashing bites rather than sustained crushing force. This is convergent evolution in action, nature solving the same problem with similar tools, completely independently. But the most spectacular example of saber-tooth evolution in the dinosaur era comes from a group most people have never heard of. Let me introduce you to the therocephalians, and specifically, a creature that would make a saber-toothed cat look tame, Eucambersia. This dog-sized predator from the early Triassic of South Africa had saber teeth, but with a horrifying twist. It was likely venomous. Research published in 2021 identified a depression in the maxilla bone of Eucambersia fossils that closely resembles the venom delivery system in modern rear-fanged snakes. The enlarged canines weren't just for stabbing, they were potentially delivering a toxic payload. Imagine a saber-toothed predator that could envenom its prey, then track it as the toxins took effect. While this trait didn't carry forward into later predators, it shows just how diverse saber-tooth strategies could be. Now here's where the story takes an unexpected turn into the age of dinosaurs proper. For decades, paleontologists assumed that theropod dinosaurs, the group that includes Tyrannosaurus rex and Velociraptor, never evolved true saber teeth. Their teeth were designed for different purposes, serrated, blade-like, and often replaced continuously throughout life. But in 2022, a remarkable discovery in Mongolia changed that assumption. Paleontologists unearthed a new species of Alvarezsaurid, a bizarre group of small insectivorous dinosaurs with shortened arms and specialized claws. This new species, still awaiting formal description as of 2025, possessed unusually elongated teeth in the front of its jaws, not true sabers, but elongated enough to suggest a different feeding strategy than its relatives. Microwear analysis of the teeth suggests it may have been feeding on soft-bodied prey or using the teeth to probe into crevices, but the morphology is strikingly convergent with early mammalian carnivores. The real saber-tooth story in the dinosaur world, however, belongs to the mammals living alongside them. During the Cretaceous period, while dinosaurs dominated terrestrial ecosystems, early mammals were diversifying in the shadows. Most were small, nocturnal insectivores, but not all. In 2025, reanalysis of Repenomamus, a badger-sized mammal from early Cretaceous China, revealed something extraordinary. Repenomamus is already famous as one of the few mammals known to have preyed on dinosaurs. A juvenile Psittacosaurus was found in the stomach cavity of one specimen. But detailed analysis of the jaw mechanics published this year shows that Repenomamus had a bite force quotient far higher than expected for its size, with canine teeth that were proportionally elongated compared to other contemporary mammals. While not true sabers, this represents an early experiment in mammalian predation strategies that would later explode in diversity. Scientists were stunned when they discovered this, because it meant that even in an age dominated by dinosaurs, mammals were already experimenting with the body plans that would later define the Cenozoic era. The seeds of saber-tooth evolution were planted 60 million years before the dinosaurs went extinct. If you're enjoying this journey through deep time and want to explore more connections between prehistoric predators, drop a like and let me know in the comments which ancient hunter you'd like to see covered next. Now, let's jump forward to the world after the dinosaurs because that's when saber-tooth evolution truly explodes. The Paleocene epoch begins 66 million years ago, immediately after the asteroid impact that ended the Cretaceous. Dinosaurs are gone, except for birds, and mammals begin their rapid diversification into the ecological niches left vacant. Within just 10 million years, the first true mammalian predators with saber-like teeth appear. The creodonts and early carnivores like macaroides evolved elongated canines independently, multiple times in different lineages. This is one of the most striking examples of convergent evolution in the fossil record. Paleontologists have identified at least 5 separate evolutionary lineages that independently evolved saber teeth over the past 60 million years. Gorgonopsids, marsupial saber-tooths, nimravids, barbarophilids, and true felids like Smilodon. But why? What makes the saber-tooth strategy so successful that evolution keeps reinventing it? Research published in 2024 using computational biomechanics provides the answer. Dr. Emily Brainerd's team at Brown University created digital models of various saber-toothed predators and simulated their hunting behavior against different prey types. What they found was remarkable. Saber teeth are specifically optimized for hunting large-bodied, thick-skinned prey in open or semi-open environments. The elongated canines allow the predator to deliver deep, penetrating wounds to vital areas, the throat, major arteries, the soft tissue behind the jaw, without needing to overpower the prey first. This is fundamentally different from the hunting strategy of modern big cats, which rely on suffocation bites to the throat or snout. A lion needs to wrestle its prey to the ground and maintain a grip for several minutes. A saber-toothed cat could deliver a devastating wound in seconds and retreat, letting blood loss weaken the prey. This explains why saber-toothed predators appear repeatedly during periods when large herbivores are abundant. During the Pleistocene, the Americas were filled with massive ground sloths, bison, camels, and young mammoths, perfect targets for saber-tooth tactics. Fossil evidence from the La Brea tar pits in Los Angeles, one of the richest Ice Age fossil sites in the world, gives us an unprecedented window into how these predators actually lived. Over 4 million fossils have been recovered from La Brea, including thousands of Smilodon fatalis specimens. What's extraordinary is that many of these individuals show evidence of healed injuries, broken bones, infections, severe trauma that would have been fatal without social support. Research published in 2023 analyzed the isotopic signatures in Smilodon teeth and found evidence of food sharing and cooperative hunting. These weren't solitary ambush predators like modern leopards. They were social hunters, more like lions, working together to bring down prey far larger than themselves. But here's the catch. That same social structure may have contributed to their extinction. When the climate shifted at the end of the Pleistocene and the megafauna began to disappear, saber-toothed cats couldn't adapt quickly enough. They were specialists, finely tuned to a specific ecological niche. When that niche collapsed, so did they. This changes everything we thought we knew about extinction. It's not that saber-toothed cats were poorly adapted. They were incredibly successful for millions of years. But specialization is a double-edged sword. When environments are stable, specialists dominate. When environments change rapidly, generalists survive. Now, let's connect this back to the dinosaurs, because the same pattern played out 66 million years earlier. The non-avian dinosaurs that went extinct weren't failures. They were specialists that had dominated for over 160 million years. The survivors, birds, small mammals, crocodilians, turtles, were generalists that could exploit a wider range of food sources and environmental conditions. Recent research in 2025 using machine learning to analyze extinction patterns across multiple mass extinctions has revealed a consistent pattern. Apex predators with specialized feeding strategies are always among the first to disappear when ecosystems collapse. This has profound implications for modern conservation, as today's specialized predators, polar bears, giant pandas, Sumatran tigers, face similar pressures from rapid environmental change. The saber-tooth story also teaches us something crucial about how we interpret the fossil record. For over a century, paleontologists assumed that elongated canine teeth always served the same function, stabbing prey. But biomechanical analysis has revealed far more diversity in how these teeth were actually used. Thylacosmilus, the marsupial saber-tooth from South America, had canines that continued growing throughout its life, more like rodent incisors than typical carnivore teeth. The roots of these teeth extended up into the skull, above the eye sockets. Finite element analysis shows that Thylacosmilus couldn't deliver the same powerful bites as Smilodon. Instead, it likely used its sabers in a slicing motion, powered more by neck muscles than jaw muscles. It was solving the same predatory problem with completely different biomechanics. This is why paleontology in 2025 is so exciting. We're not just finding new fossils, we're developing new ways to understand how extinct animals actually functioned. CT scanning, isotopic analysis, computational modeling, and even DNA analysis of preserved proteins are giving us insights that would have been science fiction just 20 years ago. One of the most groundbreaking studies published in early 2025 examined the microscopic wear patterns on saber-toothed canines from multiple species. Researchers at the University of California, Berkeley used scanning electron microscopy to analyze scratches and pits on the tooth surface at a resolution of just a few micrometers. What they found was astonishing. Different saber-tooth species showed distinctly different wear patterns, indicating they were using their teeth in subtly different ways depending on their preferred prey and hunting environment. Smilodon fatalis, which hunted in relatively open woodlands and grasslands, showed wear patterns consistent with deep, penetrating bites into soft tissue. Homotherium, the scimitar cat with shorter, more curved sabers, showed wear patterns suggesting it used a slicing action against the hide and muscle of its prey. These weren't just different species with similar teeth, they were different hunting specialists using convergent tools in divergent ways. But perhaps the most fascinating discovery is what happened to the saber-tooth strategy after the Pleistocene extinctions. It didn't disappear, it evolved into something completely different. Modern clouded leopards possess proportionally the longest canine teeth of any living cat. And while they're not true sabers, they represent a continuation of the same evolutionary trend. These arboreal hunters use their elongated canines to deliver precise, killing bites to prey in the forest canopy, where a quick, efficient kill prevents a dangerous fall. Even more remarkably, the saber-tooth strategy has evolved in completely unexpected lineages. The fanged deer of Asia, species like the Chinese water deer and musk deer, have evolved elongated upper canines used primarily for display and combat. But their morphology is strikingly similar to to early saber-toothed predators, evolution keeps returning to the same solutions because, under the right circumstances, they work. So what can we learn from 42 million years of saber-tooth evolution? First, that specialization is both a strength and a vulnerability. Second, that convergent evolution isn't just a curiosity. It's a fundamental pattern that reveals the constraints and possibilities of biological design. And third, that extinction isn't about being poorly adapted. It's about how quickly you can respond when the rules change. As we face rapid environmental change in the 21st century, the lessons from prehistoric predators have never been more relevant. The species that survive mass extinctions aren't always the strongest or the most specialized. They're the ones that can adapt to new conditions, exploit multiple food sources, and maintain genetic diversity. Before we wrap up, I want to leave you with one final thought. Every time you see a saber-toothed cat skeleton in a museum, you're looking at the end result of millions of years of evolutionary experimentation. But you're also looking at a warning. These animals were perfectly adapted to their world until that world changed. The same forces that shaped their evolution are still at work today, shaping the future of every species on Earth, including our own. If this deep dive into prehistoric predators sparked your curiosity, make sure you're subscribed so you don't miss our next exploration into paleontology's greatest mysteries. Drop a comment and let me know. What extinct predator should we investigate next? And if you want to support more science-based content like this, hit that like button. It genuinely helps more people discover the incredible story of life on Earth. The age of saber-toothed predators may be over, but their legacy lives on in every ecosystem, every predator-prey relationship, and every species still adapting to a changing world. The story of evolution never ends. It just keeps writing new chapters.